Hello everyone, welcome back to Networks class. So last time in class we discussed the critical path method, and that was this business about if I have a bunch of tasks and they have some prerequisites and each has a particular execution time, how long would it take me to get all of them done? And that motivated also a particular algorithm. So to solve this critical path method, we created a graph where we had negative lengths on the edges, and Dijkstra's algorithm could potentially mess up when there's negative length edges. And so we looked at an algorithm, the directed acyclic graph shortest path algorithm, that does shortest paths and directed acyclic graph regardless of whether the edges are positive or negative. And just one other thing I want to mention about this is that there is a third algorithm that basically works in any graph as long as there's no negative length cycle. It's called the Bellman-Ford algorithm. And we don't really teach it in class because it doesn't get used that often. And it's also reasonably slow. So its running time is O of n times m, which is significantly slower than both Dijkstra and the DAG shortest path algorithm. But if you're interested or curious, you can go and look up the Bellman-Ford algorithm and find out some more about it. So the plan for today is the following. So first we're going to go over a little bit just the modeling in GAM0. And then we're going to look at our last shortest path algorithm that we'll call Astar search. And Astar search is going to basically address some other things about Dijkstra's algorithm that are a little bit unsatisfying. So let's first talk about the GAMS homework assignment. So in this homework assignment, we had to create an expansion plan for this company that required a minimum number of machines for various years. So the plan here is, or the way to create the graph is something like this. So at the beginning, we start in year 0 with 0 machines. And out of this position, out of year 0, 0 machines, we technically have 4 actions. So the actions are buy 0 machines, buy 1 machine, buy 2 machines, or buy 3 machines. So those are the 4 actions we have because we cannot buy more than 3 machines, just anywhere between 0 and 3. And so each of these actions leads us to a different position. So if we buy 0 machines, we would be in year 1 with 0 machines. If we buy 1 machine, we would be in year 1 with 1 machine. So year 1 with 1 machine. If we buy 2, we would be in year 1 with 2 machines. And if we buy 3, we would be in year 1 with 3 machines. But now the issue is that for each year there's a minimum number of machines that we need. So for year 1 we have to have 1 machine. And so what we're going to do is we're going to just delete the nodes that don't satisfy these minimum criteria. So we can't be in this node year 1 with machine 0. We want to disallow that. So what we're going to do is we're just going to delete that node and all of the edges that come in and out of it. And so that leaves us with a graph like this, and of course, you can expand this into the future. So that's the basic idea, and the start node here would be year 0, machine 0, and the end node would be something like year 6, machine 8, because that's the position in which we want the company to end. And really, the modeling method that gets used for solving this problem, it's very, very common. It's called dynamic programming. And the basic idea behind it is the following, that a node is kind of a state of the system. So in particular, the state here is what year we're in and how many machines we own. And an action creates an edge. So for example, we can take the action of buying 2 machines, and that transfers the state of the system from year 0, machine 0, to year 1, machine 2. So this is very, very common. And in class, we're really only looking at the most basic kind of dynamic programming. In general, an action could potentially give us a probability distribution on future states. So in everything that we're doing in class, an action deterministically transfers us to a particular state. But there could be some randomness involved, and that's also considered dynamic programming. So really, you can run entire courses on dynamic programming. It's very, very useful. It appears in just hundreds of applications. So one application, for example, is this is the way that airlines price airplane tickets. So the actions there would be what price we can set for the ticket, and that creates a probability distribution in terms of how many people are going to order seats, and then that takes me to a new state, which is how many seats are left on the plane. So that's just one example of an application for dynamic programming. So that's the basic idea for solving GAM0. There's a solution online that you can go and take a look at if you need to. So let's move on to the main content of today's lecture, which is the Astar search algorithm. So to do this, let's consider to motivate Astar search, let's consider a particular example. So suppose that we're Google Maps, and someone asks us for a route from Monterey to Austin. And maybe here's Seattle. And so let's say that we're using Dijkstra's algorithm to try to find the shortest path. Well, we know that Dijkstra's algorithm kind of proceeds in these concentric circles. So it's going to explore the graph kind of like this. And the point is that it's going to find us a route to Seattle way earlier than it finds us a route to Austin. So Dijkstra's algorithm is doing all of this extra work that's unnecessary because it's exploring the graph to the north when we know that Austin is to the east of Monterey. So the reason that Dijkstra's algorithm is doing this is because it's worried about some kind of black hole. So it's worried about some kind of edge over here that could potentially have length 0. And so that's why if there is such an edge, we have to look at Seattle because we might potentially find a teleporter over there that'll teleport us to Austin. And so that would be the shortest path. But we know in reality this doesn't happen. So can we somehow go in and fix our algorithm? So the basic idea is that we'd like to have an algorithm that works more like this. So if this is Monterey and that's Austin and this is Seattle, we'd like an algorithm that just generally looks in the right direction. So in this way, it wouldn't be exploring in the wrong direction towards Seattle, but it would just head towards Austin and would find us a route towards Austin. But to do this, we have to provide the algorithm with a sense of direction. And the way that we're going to provide this sense of direction is with an estimate function. So the estimate function is just going to take in a node u and the destination. So this is where we're going. And it's going to returns an estimate of the distance. So the kinds of possible estimates that we might have for a problem like this would be something like the Cartesian or Euclidean distance between lat long locations. Or another one that would be just as well would be something like the great circle distance between the two nodes, because we know that a path using the highways has to be only potentially longer than this great circle distance. But the key to these estimate functions is that they have to be an underestimate. So we're not allowed to overestimate the path from Monterey to Austin. And both of these functions right here are underestimates, because the Euclidean distance underestimates. It's even a smaller underestimate than the great circle distance. And the great circle distance can only still potentially underestimate the actual distance. So the basic idea behind A star, once we have this estimate function, is the following. So we actually have two things during the algorithm. The two things that we have is this distance label from S to current node U. So that's distance label from S to U. And we also have this estimate function from U to T. So estimate from U to T. And so the idea is that we'll process nodes in the order of their total cost estimate. So what is a total cost estimate? So the total cost estimate of a path starting at S, going to U, and ending up at T. So that's starting at S, going to U, and ending up at T. Well, this is just going to be the distance from S to U, which we're estimating with this d tilde, the first thing that we have here. And the second part of this path from U to T is just going to be whatever our estimate is, which is the second piece of information here. We have estimate from U to T. So the total cost estimate is just going to be how much ever it takes me to get from S to U plus the estimate from U to T. And so the idea is to just run Dijkstra, but process nodes based on this total cost estimate order. So let's take a look at a pseudocode for A star search and then run an example that I think is going to help illustrate everything. So the pseudocode for A star search is very similar to that for Dijkstra. So it takes in as a graph G, it takes in a source node S, but it also takes in a destination node T, which is the place that we're heading. And the first few lines here look exactly the same as Dijkstra's algorithm. So let Q be an empty priority queue. We're going to initialize all nodes to white. We're going to set the color of S to gray. We're going to set the search parent of S to none. And we're going to set the distance label of S to S to be 0. So the main difference from Dijkstra's algorithm is that when we push S onto the queue, before we used to just push it on with just its distance label. But right now we're going to push it on with its distance label plus this estimate, because we want to be processing nodes in the total cost order here. So we're pushing it on with a total cost associated with that node instead of just the distance label. But after that, the algorithm continues exactly the same way as in Dijkstra. So while Q is not empty, we're going to let U equals Q dot popmin. We're going to set the distance from S to U equal to whatever the distance label is. And that's because as soon as we pop U, its distance label gets fixed. So exactly the same way as in Dijkstra's. And then over here, if U happens to equal T, then we're going to be done. So this algorithm completes as soon as the destination T gets popped off of the queue. But if U is not T, then we still have to process the new information that we're getting out of U. So for each edge UV, we're going to do the following. If V is white, then we're going to set the color of V to gray, set the search parent of V to none. We're going to set the distance label of S to V equal to whatever the distance was from S to U plus the edge that we are currently looking at, CUV. So this is also exactly the same as in Dijkstra's algorithm. So again, the only difference is that when we push V onto the priority queue, we're going to push it with its distance label plus this estimate function. If V is gray, we might potentially need to update its distance label. So if V is gray and its distance label is worse than the new information that we're seeing, then what we're going to do is we're going to set the search parent of V to U, and we're going to update the distance label. So the distance label from S to V is now going to be equal to this new better one, which is S to U plus CUV. And then we're going to decrease key on V, but the new key isn't just the distance label, it's this distance label plus the estimate. So at the end here, at the end of this for loop, we have processed all of the information for U. So here we're just going to set the color of U to black. So that is the basic pseudocode for the Astar algorithm. So really the only difference from Dijkstra's is the fact that whenever we're pushing something onto the queue, or whenever we're decreasing the key, we're always including this estimate function, which is the new information that's going to lead us roughly in the right direction. So let's run an example of A-star search to see how this algorithm works. So for an example for A-star, let's just use our same example that we used for Dijkstra's algorithm. So it was a graph that looked like this. So 0, 1, 2, 3, 4, and 5. And then 0 had a couple of edges here. So this one had distance 4, this one had distance 6, this had distance 1, distance 3, 2, 1, 1, 3, and 7. So besides getting the graph, we also need a start node. So the start node here is going to be 0, and an end node. So let's say that the end node here is 5. And the last thing we need is an estimate function. So for this example, let's assume estimate returns the exact distance to t. So this is just for an example. In real life, of course, we wouldn't have a function of this. But let's see what happens if we happen to have a function like this that happen to be very accurate in estimating the distance to the destination. Okay, so let's start the algorithm. So at the beginning on this algorithm, just s gets put onto the queue, and its distance label is 0. And for this particular example, the estimate function is going to give us 9 because that's the shortest path from 0 to 5. So in total, the total cost estimate is going to be 9. So the only thing we can do here is pop 0. So we're going to pop 0. And then when we pop 0, that's going to give us 2 new white successors. So those are node 1 and node 2. And let's figure out what distance labels we add those with. So the distance labels here are going to be whatever the distance to 0 was fixed on, which was this 0. I got fixed as soon as we popped it, plus the edge length. So for 2, we're going to have a distance label of 4. And for 1, we're going to have a distance label of 6. So let's see what the estimates are. So from 2, the estimate would be 5. And from 1, the estimate would be a 6. And so in total, for 2, we're getting 9, and for 1, we're getting 12. So since we're processing these nodes in the order of their total cost estimate, that means that the next thing we have to do is pop node 2. So let's pop node 2 and see what happens. So node 1 remains on the queue. Its distance label was 6, and its estimate was 6. So when we pop 2, we're going to see 2 new white successors, 3 and 4. So we have to add those onto the queue. And when we add them, we have to add them with some distance labels. So the distance label for 3 is going to be this 1 plus the distance I got fixed to 4, which is this 4. So the distance label here is going to be 5. And the distance label to node 4 is going to be this 3 plus the distance to node 2, which was this 4. So that's going to be a 7. Now the estimates to 4 is a 3 because that's just the shortest path from 4 to 5. And the estimate from 3 to 5 is going to be 4. So besides these 2 white successors, node 2 also has a gray successor, which is node 1. And the new information that we're getting for node 1 is this 1 plus this 4, which is a 5, which is better than the 6. So the 6 is going to get updated and decreased down to a 5. So altogether, when we sum everything here, for node 1 we get an 11, for 3 we get a 9, and for node 4 we get a 10. So that tells us, because we want to be processing always the minimum node out of these, that we have to pop node 3 next. So what's going to remain on the queue is just node 1 and node 4. And their current distance labels are 5 for node 1 and 7 for node 4. Their estimates are 6 for node 1 and 3 for node 4. So when we look at node 3 here, it's going to have one successor, which is node 5, so we have to add that on. And the distance label for node 5 is going to be this 7 plus this 5, because that's what the distance to 3 got fixed to. So 7 plus this 5 gives us a 12. And the estimate from 5 to itself is just going to be 0. So besides this white successor, node 3 also has a couple of gray successors, 4 and 1. So let's see what we're getting for 4. We're getting this 1 plus this 5, which was a 6. That was better than the 7. So this is going to get updated to a 6. For node 1, we're getting a 2 plus a 5, which is a 7. Now that's worse than this 5, so we're no updates over there. So that completes all the edges for node 3. And so now we can sum these things up. So that gives us a 12, this is a 9, and that is an 11. So this tells us that we should be popping node 4 next. Okay, so what remains on the queue here is node 1 and node 5. And their distance labels are 5 for node 1 and 12 for node 5. The estimates are 6 for node 1 and 0 for node 5. So let's see what happens when we look at node 4. It only has one gray successor, which is node 5. And the new information that we're getting for node 5 is this 3 plus this 6, which is 9. And that 9 is better than this 12. So we'll decrease this 12 to a 9. And that completes all the edges for node 4. So in total here we're getting a 9 for node 5 and an 11 for node 1. So that tells us that we should pop node 5. And as soon as we pop node 5, the algorithm completes, because that's when t is equal to the node that we popped. And so right here we're done. So let's see some kind of general rules that we can pull out of this example. So let's see what numbers are associated with the nodes that we popped. So when we popped 0, the number associated with it was 9. When we popped 2, the number associated with it was 9. When we popped 3, the number associated with it was 9. When we popped 4, the number associated with it was 9. And when we popped 5, the number associated with it was 9. And actually, the shortest path from 0 to 5 has also length 9. And in fact, the shortest path goes from node 0 to node 2 to node 3 to node 4 to node 5. And that's exactly the sequence in which we're popping off these nodes. So first we pop node 0, then node 2, then node 3, then node 4, and then node 5. And so that's kind of one key to learn about A star. So if the estimate for A star is exact, A star simply walks down the shortest path. So if you give it an exact estimate, A star isn't going to waste any work. It's just going to take the shortest path directly to the destination. And in fact, you can prove this, that there is no algorithm that looks at less nodes and finds a shortest path from S to T, given these two assumptions, that we have non-negative length edges and the estimate function. So in some sense, A star is really the fastest algorithm that you can have for shortest path. So given the estimate functions, there's no other algorithm that works faster. So here's another thing to consider. So if the estimate function returns always 0, so that's kind of the simplest underestimate we can have, is just whenever you ask me for an estimate, I'll say, oh, 0. But what happens if these estimate functions are just return 0? So all of these bottom numbers here would be zeros, which means that we would really be processing nodes in order of their d tildes. And processing nodes in order of the d tildes, what that does is it just it makes A star run in the same way as Dijkstra. Because A star is going to process the nodes in exactly the same order as Dijkstra's algorithm is going to be. And in fact, if this estimate function is just any constant, then still the only thing that's differentiating between the different nodes is the d tilde, and so you're going to get Dijkstra's algorithm back. So if we try to sort of play some kind of trick and just give a constant estimate function, we're not going to get anything better. What really makes this A* work for the Monterey to Austin example, so if this is Monterey and Austin is here and Seattle is here, what makes A* work is that the estimates to the north are going to be worse than the estimates towards Austin. And so that's what makes A* really explore towards Austin first instead of wasting its time and going north to Seattle. So here's a few other sort of things to point out about A*, or just some comments about A* in general. So first, let's see. So if we could use Great Circle or Euclidean distance, which is better? Well, so we know if we had the exact estimate, we would just walk right down the shortest path and we'd get something very fast. We know if we had this kind of silly constant estimate that just gives you a 0, then you just get back Dijkstra's algorithm. So between these two estimate functions, Great Circle and Euclidean distance, Great Circle is the closest to the true path length without going over. So closest without going over. So really, you'd prefer to use Great Circle because that's going to lead you more in the right direction than Euclidean distance will. And so you can think of this, if you have multiple estimates for your paths, you can think of this as kind of a Price is Right kind of thing. You want the closest estimate to the real distance without going over the real distance. And the closer you get to that true distance, the faster this algorithm is going to run. So now let's just do one more example, which is suppose that, just to understand why you have to underestimate. So if I'm allowed to overestimate, how can I make the path from Monterey to Austin kind of go up through Canada and come back down in Austin? So we can do this by just putting 0 estimates on all of the nodes on this path and putting infinite estimates everywhere else. So what this is going to do is that when the algorithm puts a bunch of nodes around the start node, only one node is going to have distance label plus estimate that's smallest, which is going to be the one on this path. And similar things going to happen around here. So what's going to happen is we're just going to be pushing nodes on this path. They're always going to have a smaller sum of estimate plus distance label than everything around them, because around them everything is going to have this infinite estimate. And so that's going to force the algorithm to go around through Canada, get to Austin. As soon as it pops off Austin, it says that it's done. And so overestimating can lead to wrong answers. So that's the basic idea behind A* search and why we have to have underestimating distance functions. So one last thing to comment about A* is let's just talk about A*'s running time. Now, A* really is the exact same algorithm as Dijkstra's algorithm, except for one small difference. The small difference is just that we have to compute these estimate functions. So let's imagine that these nodes here have latitude and longitude locations. Well, computing the estimate function, if that's a great circle distance, is just very fast. It's just O of 1, blazingly fast, because it's just a few additions and subtractions. And so the runtime for A star is the same as Dijkstra's. In the worst case. So computing these estimates doesn't really add too much cost to everything, but potentially it works a lot faster. If we have a good estimate function. And so if you were going out and programming a Google Maps or something like that, and you had a gigantic graph in which you wanted to find shortest paths, you really want to be running A star instead of Dijkstra's algorithm. So thanks a lot for listening. That concludes lecture for today, and I'll see you all next time.